So we will start off with differential equations. Differential equations are extremely important for engineering students. In fact, all the dynamical systems, RLC circuits, beams which undergoes bending, and any object which undergoes vibration are modeled using differential equations. So in the introduction, we are going to look at what a differential equation is, and then we are going to see what the order and the degree of a differential equation are, and then the nature of the solution of a differential equation, and then finally initial value problems and boundary value problems. So first, a differential equation is an equation consisting of these type of terms, derivative terms. Now for example, this is a differential equation because of this term. This is a differential equation because there are two derivative terms here, right. Now we will see what the order and the degree of a differential equation are. Now let us go through 4 examples. The degree, first I will take up the order. The order of a differential equation is the order of the highest derivative term appearing in the differential equation. For example, in this case, this is the highest derivative term. This is the first order, this is the second order. So this is the first derivative, this is the second derivative. So you obtain this after differentiating y twice. Therefore, the order is 2. Here, even though you have a number appearing here, it is the cube of the first derivative. So still the highest derivative term is this one. Again, it is a differential equation of order 2 because of this. This is the highest derivative term, not this one, because this is the first derivative, this is the second derivative. In the third case, this is the only term appearing here, and its order is 4. Therefore, the differential equation is of order 4. In this case, there are two terms like this, both are of like order 2, this is the second derivative, this is the second derivative. How? Therefore, order is 2. Now if you take up the degree of a differential equation is the following. You take the highest derivative term. The power of the highest derivative term is called the degree of the differential equation. For example, this is the highest order term, the power is 1, therefore degree is 1. This is the highest order term, again the power of this term is 1, therefore the degree is 1. Here, this is the only term, its power is 1. It is a fourth order term, but power is 1. It is traced to its first power, power is 1, therefore degree is 1. But here, there are two derivative terms, both are of the same order, 2, 2. However, this is raised to its third power, therefore the degree is 3, right. Now let us get into the solution of a differential equation. Let us first take up, take an algebraic equation. Now if you start with this, x is equal to 3, you can construct this equation. Here you multiply both sides by 2, then you subtract 1 from both sides, divide both sides by 5, then again add these two equations to get this one. So if you try to solve this, you will get x is equal to 3. This is the solution. Here the solution gives you some value to the variable, but in the case of a differential equation, the solution is different. There, you take this one for example, if you differentiate this, you will end up with this. When you get the second derivative, you get this one. So this is a differential equation of order 2. This is the differential equation of order 1. Now if you try to find the solution, you go back and try to figure out from which function that this is originated, like this differential equation originated, right. It is like this, it is like a DNA test, like once you have a child, how do you determine the parent, like that, from where it is originated, like. Now this equation is, this differential equation is obtained from this function. Here as the solution of a solution to a differential equation is not a value, it is a function, right. That is the difference. In the case of an algebraic equation, you get some value to the variable as the solution, but in this case you get some function as the solution. So, this is how you solve it in this straightforward example, like you take this, you write this as the derivative of the first derivative. Now, you integrate both sides. So, this is what you put the integral sign and dx in addition. So, you have the same thing in the right hand side. So, these two will go away with d and the integral sign, leaving this part in the left hand side. Right hand side you get 2x plus c1. Now, again if you integrate this, you will end up with like here you get, from this you get x squared, from this you get c1x, and you get some arbitrary constant c2. From the left hand side you get y. Now, this is the function. So, I mean here c1 and c2 are arbitrary constants. Now, you have a little problem. Now, you might say, okay, this is a function that you have originated from. Now, you will end up with something similar, but not the same. Yes, because this will cover all possible original functions that will generate 2 as the second derivative. Like for example, if you start off with this one, say for example x squared plus x plus 7, still you will end up with this one, and the second derivative will be this, right. If you have for example 4 here, you get a different first derivative would be different, 2x plus 4, but still the second derivative will be 2. So, that is why this will cover all possible such solutions, all possible such functions that will give you 2 as the second derivative, not the special function that you have selected, right. That is the difference, right. But if you give some conditions on this one, then you can figure out C1 and C2. Otherwise, you will get this general solution. And also there is one thing that you need to note down, like here there are 2 arbitrary constants, right, and also what is the ODE of the differential equation? The ODE is 2. Always the number of arbitrary constants you get in the solution is equal to the ODE of the differential equation, right. And also if you want to determine these arbitrary constants, you need to be given some conditions, right. Based on that concept, there are 2 classes of differential equations you might encounter. So, we are getting into that part now. Those are called initial value problems and boundary value problems. First, let us take initial value problems, usually abbreviated by IVPs. We will take up this solution. Here, other than this differential equation itself, you get some conditions. The number of conditions should be equal to the ODE of the differential equation. Like if you have a first order, then you need only 1 condition. If you have third order, you need 3 conditions. They are called initial value problems because these are the you have all the conditions when the variable is equal to 0, when the independent variable is equal to 0, when x is equal to 0. If the variable is t here, if the independent variable is the time variable, then you get all initial values, like initial value of the function, initial derivative of the function, right. Now, you have this, there are 2 conditions, the number of conditions are equal to the ODE of the differential equation, because the reason is that the number of arbitrary constants is equal to the ODE of the differential equation. Therefore, to determine those arbitrary constants, you need that many initial conditions. Now, a solution is like this. This is the differential equation we considered in the previous section. Therefore, you know the solution. You first find the solution. Without, just by ignoring these 2, you find the solution. Now, this is the solution which satisfies this one. However, if you impose these 2 conditions, you can find C1 and C2, right. Using initial conditions, you can find C1 and C2. How? This is your y of x, right. Now, initial condition, always the values are given when x is equal to 0. Plug in x is equal to 0, you will get this. Now, y naught is equal to 0, therefore you plug in 0 there, 0 is equal to C2. Now, value of C2 is known. Now, you have this again, get the derivative, this is the general solution, get the derivative. Now, you plug in 0 for x because you have y dash 0 here. Now, to use that you need to have y dash, now plug in 0. Now, since y dash naught is equal to 1, you plug in that, you will get C1 is equal to 1. So, now plug in those values in the general solution, C1 is 1 and C2 is 2, sorry, I am sorry, C2 is 0. So, C1 is 1, constant term is 0. So, this is the solution. So, that is a special solution for that problem and this is the general solution, right. Now, if you go for the next one, boundary value problems, like you might encounter boundary value problems when you deal with beam bending, because take this as the beam. Now, if you measure x as this axis, now this is the value of x at 0, this is the value of x at the beam length, let the length is L, then this x of L, x at L, right. So, you have various conditions like the displacement or the slope or sometimes shear stress or bending moment like that. So, you have various conditions at the ends. So, all those conditions are not at 0. Sometimes you might have a condition at 0, but all the conditions are not given at 0. There should be at least one condition which is not at 0. Here the value is at 3. Therefore, in this case again the same differential equation, for the sake of simplicity I considered the same thing. So, you will end up with this as the general solution where C1 and C2 are arbitrary constants. Now, you can use these boundary conditions to determine C1 and C2. How would you do that? Okay, again take this one. To use that you have to plug in 0 for x, you will get this. Now, since y naught is 2, you plug in 2 there, right hand side is C2, therefore, C2 is equal to 2. Now, to use this one, plug in x is equal to 3, so you will get this. Now, y3 is equal to 6, therefore, you plug in 6 there, you will end up with this, giving you C1 is equal to minus 5 over 3. Now, plug in the values for C1 and C2 in this general equation, general solution, to get the solution to the boundary value problem. And always there is a theorem saying existence and uniqueness of differential equations. It says that if you have an initial value problem, no matter what the equation is, you always have a solution like this, a unique solution. Remember that this is not a unique solution, because by varying these arbitrary constants, you can generate infinite number of solutions. But here it is free from arbitrary constants, therefore, it is a unique solution. That theorem says that for every initial value problem, you have a unique solution. There exists a solution and also it is unique. Okay. Basically, this is the introduction. In the next section, second section, we consider the first order differential equations. So, I will meet you there. Right? Okay. Thank you.